we know that the standard knapsack problem is not that easy to solve, but in this question, we're trying to show that for the simplified version of problem with unlimited number of copy for each item, we should be able to solve it in polynomial time. And also we are going to introduce an algorithm for solving this problem. I'll give maybe 1 or 2 minutes for you to think about it. And at the same time, I'll maybe just draw a quick example containing multiple elements, and then we'll then try to find out how we may solve this problem, this simplified problem, in polynomial time. For this question, remember that we have a limited amount of capacity we have, that we want to load some copy of these elements to make sure that we can maximize the total value that we load. But of course, we want to make sure that the total weight of the elements we load should not exceed the capacity we have. For example, in this task, if we have 3 different items, item 1, item 2, item 3, we may load item 1 and item 2 once. So we have total weight of 4 plus 5 is 9, smaller than 10, so it's valid. And the total value in this case would be 11 plus 12, giving us 13. But of course, for this question where we have unlimited copy of each item, looks like it's trivial to say, let's load item 2 twice. So the total weight would be 5 plus 5 equals to 10. And the total value would be 12 plus 12, giving us 24. So that's better than the previous option we have. Now, of course, we may also say, let's load item 3 times, but I think that will only give us 21 as the total value. Now, how do we find the highest value that we can get? I think we can also use a dynamic programming approach. So of course, without using dynamic programming approach, we may again use an approach like brute force to try all possibilities. Let's say we'll consider if item 1 is loaded once, 0 times, once, twice. Then for the remaining capacity, we can consider if item 2 is loaded 0 times, 1 times, 2 times until we reach the capacity. And then for the remaining capacity, we consider item 3. So this brute force approach, of course, will give us a correct solution, but I think the complexity would be exponential as well. Now let's consider about a dynamic programming approach. Now in our case, the capacity is 10, so I'm going to create an array starting from 0 to 10, which is the capacity we have. And I'll also have another array V, and the purpose of having V here is that VI tells us that VI tells us the maximum value we can get when we have the capacity of I. And I think clearly V0 should be 0. So we have total capacity 0, so we can't load anything. Of course, the total value would be 0. And clearly, if we have 1 as a capacity, in our case, all 3 items has the weight greater than 1, so we can't load anything. So again, we get a 0. And similarly for capacity of 2, we can't load anything, so that's another 0. Now for capacity 3, if we have 3 as a capacity, what do we have? Looks like we can load item 3 once. And if we load item 3 once, we're going to have 7 as the total value. Now for capacity equals to 4, I think we have several options. And let's try to consider these options. If we have capacity 4, I think the first possibility is we're trying to see if there is a single item that has a weight of 4. And the second possibility is that if we have total capacity of 4, rather than loading a single element, we're going to consider, or we're going to split this capacity into 2 smaller parts. Maybe we can consider 3 plus 1. That means we have total capacity of 4, but we are considering it as 2 separate bags. One bag with capacity 3 and the other bag with capacity 1. And of course, we can also do the split as 2 plus 2. So we are splitting capacity 4 into 2 bags, and each of the bag has capacity of 2. And looks like we don't need to do any other splits because we may do 1 plus 3, but 1 plus 3 will be same as 3 plus 1. So I think if we have capacity 4, we only need to consider these 3 different scenarios. For the first scenario, of course, we have an item having weight of 4, which will give us 11 as the total value. And for the second one, if we are splitting the space into 3 plus 1, then I think the problem becomes, what is the highest value we can get if we have capacity 3, plus what's the highest value we can get if we have capacity 1? And looks like these 2 problems has been solved already. If we have capacity 3, we know the value could be 7. That's the best we can do. And if we have capacity 1, the highest value would be 0. So if we do this split, I think the best we can do would be 7 plus 0, giving us 7. And for 2 plus 2 split, it means we want to find out what is the highest value we can get if we have capacity 2, plus the highest value we have if we have capacity 2. And we know from the array V that if we have capacity 2, the highest value we can get is 0. So this option will just give us 0. Now, if we have total capacity 4, we have these 3 options. And of course, it means if we have capacity 4, we're going to load item 1 into it, get the value equal to 11. Keep going. Now, if we consider the next option when we have total capacity of 5, I think we'll be considering if we are loading the item, one single item with weight equals to 5, and we will also try to split the space in these two different ways. We can also do 2 plus 3 and 1 plus 4, but they are already considered. If we are just loading a single item with weight equals to 5, the value we get is 12. If we split the space into two bags having capacity equals to 4 and 1, then we have the best we can do at capacity 4 and the best we can do at capacity 1 is give us 11. And the last one, it gives us 7. That's 7 plus 0. So this means that if we have capacity equals to 5, the best we can do is 12. So now it looks like for each of the remaining capacity I, we will consider if we have a single item taking I amount of space. If so, we're going to find out what's the total value, or what's the value of that item having weight of I. And we will also consider the split, giving us I minus 1 plus 1. The best we can do, if the capacity is I minus 1, we should have already calculated it. And the highest value we have for capacity 1, we should have already calculated it. And of course, we will also do I minus 2 plus 2 and I minus 3 plus 3, and so on. And I think the last option we're going to consider is roughly half of I, round down, plus roughly half of I, but round up. And by comparing the results of all these combinations, we're going to get the highest value we can get if the capacity is I. So when we have the capacity equals to 6, I think the best we can do would be split it into two bags, and each bag has the capacity of 3. So this will give us 14 as the total capacity. As the total value. And if we have 7 as the total capacity, I think we're going to do 3 plus 4, and this will give us 18 as the total value. And when we have 8, we can do 3 plus 5, that will give us 19, or 4 plus 4, giving us 22. And when we have capacity equals to 9, I think the best option would be load item 1 and item 2 exactly once. So we're splitting the space into two bags, one bag having capacity 4, the other